think about it.
I've been looking at it all day. I'm so lost in it.
Yeah, but really all it is.
I know when I got all forwards and then structure that you do like
You have you only have three variables. You have the size.
Yeah. But it said like construct that vector A and then the sliding directions A. How did you have any
You just
like
multiply it.
Thursday?
Oh, that was not second. That was me looking on the internet trying to
That's your last class.
Oh, okay, that's what there is.
Oh, to the exam?
Yeah.
I had to hold back laughing at it.
Right before that.
He was like
Everybody, please pick up a piece of one of these. We're going to discuss this. Just a piece, just one sheet.
Like a corner?
Mr. Hopkins. It might not be enough to read.
I literally walked into my room, took a shower, and just as soon as
right after.
Oh. Yeah. I'm so tired. I'm still tired.
There's no way you can all be great. Yeah. That was like during the class, and then 2 days later, the next day of class, like 8 o'clock at night to the next day. If I was a teacher, I would not just start it yet. Yeah.
That's what all my teachers do. Procrastinate until the next day.
Just read it. And grab one of those too.
Do you have a little nerf board?
Okay, let's see. Let's begin. This is a nice quote. The greatest kindness one can render to any man consists in leading him from error to truth. Remember, what are we made for? Remember, truth. The mind is ordered to truth. It seeks out the truth like a cheetah seeks out food. The mind seeks out truth. Okay, let's see. So on some of you, many of you in the homework that I just passed back, I wrote on the top, redo 1820 A and B because there were a lot of, I think, whiffs on that, on those problems. Didn't quite understand what was going on. So please redo those. Some of you may have gotten full credit on the homework, but I still want you to redo those, turn it in. Okay, just because you need to know those problems better. So maybe you kind of got it more or less, but I still want better. Remember, pizza on Thursday evening, 7 p.m. Don't know where yet. We'll let you know. Let's discuss dimensional analysis for Chapter 3. Now, previously we had introduced, for example, the measure of a place, measure of a location, the distance from a reference point. And we say that that is a type of length. Regardless of what system of units you use, whether it's English, SI, CGS, whatever, it's a length. And in a similar way, we can have a reference. We can make a measurement of time by referring to something which is changing. And you'll want one of these too. So we're making a measurement of time, and we call that a basic type time, any measurements of time. So a velocity, which is a derivative for example, an instantaneous velocity, which is the derivative of the position or location versus time, what is the dimensionality of that thing? Well, remember from the derivative is a ratio, and so it's the ratio of the two objects, one on the top and one on the bottom, so it's a length per time. Okay, now we've introduced, and that's all we needed for the first couple of chapters was just length. Actually, chapter 2 is about length, and then extended to time as a analogy to length. We quantified time in that sense. Now, then in chapter 3, we introduced something new. What was the new thing that we introduced in chapter 3? The most important part. Impetus, right? Whose measure is momentum. So then what is the type of momentum? Okay, so now there are a couple of different ways of doing this. And the way that would make the most sense is not the way that people generally do it. So first I'm going to show you the way that people generally do it, which is the way we're going to do it in this class, simply by weight of everybody else doing it this way. Okay, and that would be to remember that Buridan's law can be written in this form, which does not express the causal relation between velocity and momentum and mass, but nonetheless that is an equation that represents the relations between the measures. If I measure the momentum, measure the mass, measure the velocity, I can write this relation between them. And so that occurs here. We have this new thing called mass, which cannot be described in terms of a length or a time. So we'll introduce a new type called mass, in which case the type of momentum can now be expressed in terms of mass, length, and time, like this. That's the standard way. That's the way most people would recognize. That doesn't make the most sense because it's momentum that's more primary than mass. You can't really understand mass until you understand what momentum is. So it would make more sense if we were to instead define a type for momentum. I'm going to do this in red. It would make more sense, not just might. to use. Define a type called P, and then mass would be, so mass is going to be P over V, so it'd be P L inverse T, which is kind of funny. Nobody would know what you were talking about if you did that, right? That's just bizarre in terms of what's common practice. So I'm just mentioning this because I think it would be more sensible, but everybody who kind of knows dimensional analysis would look at you weird, like, what in the world are you doing there? Why would you do that? So you'd have to have an explanation for it. And in the long run, except for the fact that it emphasizes what is more primary, in terms of checking your work and that sort of stuff, it doesn't really matter. Okay, so I'm going to surrender on this one. We're going to use ML and T. So everything in the rest of this term, everything else, everything meaning all measures in this class for the rest of the term can be expressed in terms of M, L, and T. Meaning anything, so something, some physical, some quantified thing, some measure. Let me write that, some arbitrary measure. All of them can be written as M to some power, L to some power, and T to some power, without exception. Okay. And if we have two things that we want to add, A plus B, for example, if we have an equation that involves some summation of two terms, then both A and B must have the same dimensionality. Let me use some other symbols here because I just used A and B in the above thing here. So let me use x plus y, meaning some things, some measures. So if you're going to add them together, they have to have the same dimensionality. If you're going to add them together, if one is a length, the other's got to be a length. If one is dimensionless, the other one has to be dimensionless. You can't add together two things that have different types, right? Because then it would be numerically senseless. If we change system of units, we'd get a different number that isn't just simply related to the other number. Okay? Functions like cosine, sine, and exponential must have dimensionless arguments. We'll cover these later. Talk more about that. So we'll use this a lot, and so I want you to know and to remember that extra credit on all tests for doing dimensional analysis checks at appropriate places. So, for example, let's suppose we have an expression x of t is equal to x naught plus v naught t minus 1/2 gt squared. Suppose we have an expression like that. All of these terms, the left-hand side here, we are told is a length. So that means that every term, those three terms that are added together, must all have dimensionality of length. So x naught must have the same dimensionality. V naught t must have the same dimensionality. So, and the product of the dimensionality of the product is the product of the dimensionality. So if t is time, God bless, then this thing must be v naught t, and so therefore v naught must be length per time. Otherwise, the equation makes no sense. In the same way, the gt squared must have dimensionality of length. And this is, so the dimensionality of g must be length per time squared, right, to make sense out of that. Okay? So get in the habit, practice these things in your homework. Wherever there seems to be a good place to check yourself, do so. Yes?
Will we be doing nothing with temperature?
Temperature can be expressed in terms of mass, length, and time, and that will come next semester. So this semester, no, nothing with temperature, but it can be expressed as a mass, length, and time. There will be a new type next term, which is charge. That will be introduced next term. So we'll get through the entire semester with just ML and T, and then with just 4 next term, introducing temperature, introducing charge. See, you did it to me. Introducing temperature. Okay. Introducing charge. So if I have considering the rocket example, if I'm sitting on a toboggan on ice and I have a big mass and I shove that mass off, what happens to me? Yeah, go in the opposite direction. We're going to study that in some more detail. The means by which that happens is very simple, but you have an intuitive understanding of that by your own experience, especially if you've spent much time on ice. So you push it that way. And so a rocket can do the same thing by expelling part of its own mass, taking a piece of itself and shooting it out the nozzle. It will go in the opposite direction. So that's kind of the opposite of an inelastic collision. In an inelastic collision, two things come together, they stick. Heat is released. This would be the opposite. Somehow you have to introduce something into the system that causes this thing to be ejected, and the rocket will go forward. So he studies the rocket as an example of conservation of momentum. It's introduced in chapter 3. He begins by doing the wagon that's moving in the rain, so that the wagon continues to pick up. It's moving in this direction, but it's got rain coming down. So it's filling up, so its volume is changing. And so he works through this problem of the wagon accumulating, increasing in mass, and not changing in impetus because the rain doesn't change the horizontal impetus of the wagon. So it's increasing in mass and being reduced, keeping the impetus constant. Okay, so he works that problem on the way to doing the problem with the rocket, where now the rocket is expelling part of its mass. And when it does that, the rocket expels out mass with a fixed muzzle velocity. So you have the rocket here. And then the stuff comes out the back. And so what we have is two things. We have the rate of mass ejection, and the muzzle velocity, which he might call V naught. No, he doesn't.
U naught was the
Muzzle velocity.
muzzle.
It's how fast the stuff comes out the back of the rocket. Okay. So he's building up to this, and we're going to work. This is going to be for your homework on Monday. We're going to be going through this to prepare you for this. I'm not going to study the specific equations. I'm going to use it as an opportunity to describe a couple of things, but yeah. So what we're going to use this to introduce a method called direct substitution that I want you to know how to do. So you're going to use direct substitution to verify the solutions that he gets. Okay. So an example of direct substitution, and this is what this handout is about. The handout is the worksheet for your homework for Monday. So we're going to be doing this here in class. If you pay attention and work through this with us, then you should have most of your homework done for Monday. There should be very little that you need to do to get your homework ready for Monday. So let's consider an algebraic system. We have two algebraic equations. And you know the techniques for solving this. You should know the techniques. Using standard algebra for solving this system. In fact, this would involve, one way to do it would be to solve for y here and substitute into here, and then you have a quadratic equation for x, and you use the quadratic relation, quadratic formula, to find that there is in fact only one solution to this. Okay, not two, but actually only one solution. Okay, that would be the way to do it. Standard algebra. But suppose for a minute you didn't know algebra, and I could give you a solution. You could try it. So that's the direct substitution. So check that xy equals 1 over root 2. 1 over root 2. That's what I mean by direct substitution. Just plug it in. So if I'm going to label these equations A and B, then A and B become, A is 1/2 plus 1/2 is 1. Good. And the other is 1 over root 2 plus 1 over root 2 equals 2 over root 2 equals root 2. So that's good. Okay, so that is indeed a solution. Everybody okay for that? That sort of thing should be familiar to you. Checking it. Let me check another possibility. X, y is 1, 0. Let's try that. So we find out that the first one works, but the second one does not. Let's see, 1 over square root of 2. No, square root of 2. The second one does not. Right? And the techniques that you develop in your algebra class allow you to solve this without guessing. You do this, what I said was, substitute the solution, solve, eliminate y, substitute into the first one, then you have a quadratic equation, solve that for y or x, and you solve for the other one for y, and you're done. Okay, so what you've got is something similar to this in this course. We're introducing to you differential equations. And I'm not going to teach you the solution of differential equations. That's not the topic of this course. I'm going to give you solutions, but I am going to have you check them to make sure that they, in fact, do solve the differential equation. And that's what you're going to do for your homework on Monday. So let me give you some examples. You've already kind of done this, but I didn't make it explicit. Let's suppose we have x dot of t equals a constant. U is a constant. Now, that's a really easy differential equation to solve. But as I said, that's not the purpose of this class. You will probably, I think you take a course in differential equations. You just learn how to solve. There are lots of differential equations that have no explicit solution. So we really love the ones that we can solve because there are not very many of them. It's kind of surprising. So let me suggest to you, try this. Let me give it in terms of constants here. C1 and C1t plus C2. By direct substitution. Okay, anybody have an idea of how to proceed? This is analogous to what we did with the algebra. What do we do?
The derivative of C1t.
Yes, ma'am. Just take the derivative. Let's try the derivative. X dot of t. C1 and C2 are constants here. So the derivative of the term on the right, the C2, it's a constant, vanishes. The derivative of C1t just gives C1. Okay, can it be a solution?
Depends on whether C1 equals U.
Right, only if C1 equals U, right? So it's a solution if and only if C1 is U. But what about C2? Could be anything. C2 is undetermined. Okay, so you've determined that the solution is of this form plus some constant, ut plus some constant. Okay, so I gave you some of it, and you figured out a little bit more. I gave you this form, and you figured out, well, in fact, that one constant has to be u, but there's still this undetermined constant. Okay, I haven't told you how I got this. I haven't told you. You can actually go from here to here by integration. We're not going to do much integration in this term. We're going to do more in the second term. So I'm giving you, but I am going to want to study these differential equations. I'm going to give you some solutions, and you're going to start kind of corresponding solutions with differential equations. Even though you don't know the techniques of solving them, you should be able to recognize the few basic ones as you go through and know what their basic solutions are and be able to check them. Okay, so let's try another one. Let's try x double dot of t is equal to u. We're again, no, let's make that not a u. That would be kind of confusing. Let's make it negative g because we've had that one like that. Okay, so try x of t is equal to c1 plus c2t plus c3t squared. Try that. Well, actually, let's just try the same one we tried before. Let's try that one and see if that one works. So, Ms. Shaven, what do you think?
Do it twice.
Yeah, do it twice. So we get, this is what we just did, right? Only I used different, I swapped the symbols. It had C2 plus C1t. Anyway, and take the next derivative and it's 0. Can that work? Only if g is 0, right? Which is usually not what we're interested in. So this is not generally a solution. This works only if g is 0. Otherwise, no. All right, try. Let's try another solution. X of t is c1 plus c2t plus c3t squared. Let's try that one. Take the two derivatives. Everybody see that? Taking derivative with respect to time. The c's are constants. They just go along for the ride. Except for the ones, well, the derivative of a constant, of course, is 0. Okay, so can that be a solution? Only if 2c3 is equal to negative g. So only if and only if c3 is minus 1/2 g. What about c1 and c2?
They don't matter.
They're undetermined, right? c1 and c2 are undetermined as yet. As far as the problem is specified, finding a solution to the differential equation, they're undetermined. So the solution to this differential equation would be c1 plus c2t minus 1/2 gt squared. And c1 and c2 are still undetermined. They can be anything, and this will still solve the differential equation. Okay, coming to understand the idea of direct substitution.
Would x dot and x dot of t be the same thing?
Yes, sir. Right. So when I take a derivative, I generate a new function, which I call x dot of t or v of t. So yeah, it's still a new function.
So it's still x dot because it's the derivative with respect to time.
Yes, that's right.
That's what I'm implying.
So I'm being sloppy here. I could write x dot of t, x double dot of t. These are still functions of time. Remember, a derivative, the operator, takes a function and makes a new function out of it. Okay. So now you are going to consider a problem here. Let's see, which is you're going to consider this problem from the book. This is equation 3.24, or near it, 3.24. This is all detailed in the handout that I've given you. This handout is what you would download from Blackboard. I just printed it out so we could work on it in class today. So this is the worksheet on differential equations that's on the Blackboard for you. Okay, so that would be let's do rather than that one. Let's do an easier one first. I'm going to actually do the second one first. Second one's a little bit easier. So I'm going to do the second one first. So you have this. You have for a function, the velocity is a function of the mass. And I'll explain what that means here in just a second. So this is an example of the rocket. And the rocket is expelling part of its mass out the nozzle. And then you want to know how fast it's going after it still has only so much mass left. And so that's what this means. What is the velocity of the rocket after it has still only m left? It's interesting that it doesn't matter how fast it did this and the rate at which it happened. And VP there is that muzzle velocity. Okay, so this is a differential equation. You could rewrite it in a form like dy by dx is minus some constant over x. You could write it in that form, where y is a function of x. It's the same thing, just swapping symbols. Oops, I'm sorry. Right? That's the same, has the same form. The velocity is a function of mass. Well, we could say it's y is some other function of x, and we're taking the derivative with respect to its argument x. And then on the right-hand side, we get a constant over x. There's a differential equation for you. The task is to find y of x. Okay? What function has a derivative like that? So again, this particular one is not that difficult a problem to solve. This will be one of the first ones you do in differential equations. But nonetheless, you understand the idea here. It's a lot like what you did in algebra, but you're going to be using different tools. So you're going to be finding some function whose derivative is related to x in that way. Okay. Okay, so let's try something. Let's try y of x. Let's try something of the form that we just did. Let's just try one. Just try that one. Let's try this. Okay, what do we do?
Drive.
Yeah, take a derivative. Okay. Now, is there any value of C2 that's going to make that work? So this has to be true for all x. Is there any value of C2, and a is a constant there, is there any value of C2 which makes that equation true for all x? No. Not unless both a and C2 are 0, which would be the only kind of trivial case. We get 0 over 0. I can't pick any value of C2 that's going to be equal to 1 over x for any value of x. Right? There's lots of values of x I could pick there. So it's not going to work. No, doesn't work. So that's an example of one that's not going to work. Let's try another one. Let's try y of x is natural log of x. What is the derivative? Oh, that's not in your table, is it? Is it in your table? Okay, good. What's the derivative of the logarithm? 1 over x. So that's starting to look a little closer, isn't it? So what if we tried minus a log x plus b? Here, let's do some constants here rather. C1 log x plus C2. I'm sorry, y of x, excuse me. That was y of x. Let's try this. Okay, so let's try the derivative. Y prime of x is C1 over x. And I want that to be equal to minus a over x. Is there a value of C1, and I want this true for all x? I want it to be an equation, not just for a particular value of x. If it was just one value of x I was interested in, I could do it. But for all x, yeah, if C1 is negative a, then this works. So a solution of the form C2 minus a log x will work, where C2 is undetermined by the differential equation. Okay? You see how this is going? All right, now the next one is going to be a little more complicated because it involves the chain rule. You are to demonstrate that here's a differential equation. Velocity as a function of time. M naught and r are constants. I should make that a subscript. And you want to demonstrate this. Notice that the function occurs on both sides of the equation, on the left and right hand side. So this makes it a more challenging equation to solve because it occurs on both sides. It's actually not too bad. It's the next level of complexity, but it's not bad. Okay, so I'm going to here, instead of having you learn how to solve these equations, I'm going to give you the solution. And the text talks about doing it by integration, which is a method that would work here. But I want you to try this function. This is the solution. And so I want you to verify that it's a solution. In other words, when I say try, I mean verify in this case. Verify that it does solve that differential equation. So how do we proceed? Well, the v of t occurs on two sides, both the left and right-hand side. On the left-hand side, it has the derivative. So we want to take the derivative with respect to time. Okay, so let's take dv dt. We're given v of t here. All right, so v naught and m are constants. so I want to take the derivative, and so they just pass through here, and I want to take the derivative of m naught plus 1 over that. All right, now I've got to think chain rule. And that's why I saved this one for the last, so we could review how to do the little bit more complicated derivative. So let's remember what d by dx, 1 over x. The derivative of 1 over x, what is that?
Maybe 1 over x squared.
Yes, sir. Right? Remember that from the table. And you should be able to derive this one directly using the technique that we learned in the chapter by drawing the secant, making it approach the tangent, finding the slope. Okay? You can do it with that function, 1 over x. Works just fine. Okay. How about d by dx 1 over 1 plus x? What is that one?
1 over 1
So,
over 1 plus x can't be squared.
yep. Right. So, to do this, this is an example of the kind of a function of a function. And we want the derivative of the function of a function with respect to x. And the chain rule is that the derivative of a compound function like that, a function of a function, is the product of two derivatives. The first one is the derivative of the first function with respect to its own argument. And then the second one is just g prime of x. Right? The derivative of g with respect to its argument. Okay, so we have a combination here, the derivative with respect to x of 1 over 1 plus x. Oops, go back to... Okay, so that's going to be, the first thing is that we take the derivative, so let me write what the functions would be. That's the easiest thing to do, looking at this. Okay, so we can make this function 1 over 1 plus x, f of g of x, okay, could be f of some of its argument is 1 over that argument, and then g of its argument is 1 plus x. So putting these together, f of 1 plus x would be 1 over 1 plus x. Okay, so that tells you what these two functions have to be to make this work. And then f of z, f prime of z is minus 1 over z, and g prime of x is just 1. So in that case, the derivative of 1 over 1 plus x is just minus 1 over 1 plus x squared. Because the g prime is just 1. Okay. So finally, the derivative of 1 over 1 plus ax is going to be minus 1 over 1 plus ax squared. And then we need the derivative of 1 plus ax with respect to x, which is just a. Okay, so let's remember that one, and then go back to the previous equation. I need to quit extending these pages. It's going to be one long page here. All right, so what we want is the derivative d by dt. We're looking at this piece. This is what we want to do. So this is going to be minus 1 over m naught plus RT squared times R. And so the left-hand side, the derivative of the velocity is minus m naught v naught R over m naught plus RT squared. That's the left-hand side of that equation. Right-hand side was minus RV over m naught plus RT, and V is what we're checking. What we're checking here, substituting from what we're guessing, is V naught m naught over m naught plus RT. Okay, so the right-hand side then, putting it all together. Here. Okay, so this is in fact a solution of that differential equation. It involves careful use of the chain rule in taking those derivatives. Okay. So that will get you through the homework for Monday. Just about done all of it. Let's do a little bit more practice with the chain rule, just to make it something maybe you need a little more practice with. So remember this: the derivative with respect to x of f of g of x is f prime g of x times g prime of x. First, we take the derivative of f with respect to its argument, and then we take the derivative of g with respect to x, and we take the product of those. So let's do e to the ax, for example. Let's take the derivative of e to the ax. Now you know this one already. What is the derivative? But let's pretend we don't know it. You memorize that. What's the derivative of the exponential with respect to its argument? Just e to the z. So strange function, its derivative is itself. Every derivative of e to the z is e to the z. All of its derivatives are equal to itself. It's a weird function. All of it's a unique function. There's only one function that does that. Except 0, I guess. 0 is the same way. Okay, so now we have a compound function. What do we have here in this case? What is f of x, f of z, and what is g of x? So f of z is e to the z, and g of x is ax, right? So we have e to the ax. So doing that, then, let's write the derivative of e to the ax. First, it's going to be e to the z, which is e to the ax, and then the derivative, what is g prime of x? If g of x is ax, what is its derivative? A. So e to the ax times a, which is the one you were supposed to memorize from the table. Okay. That's probably good for now. Any questions about that?
Well, I was a little curious about it on the test, because with the e to the ax and all that, on the derivative table you gave us, it was just e to the x. The a wasn't there. It confused me a little bit at first, but I guess it's the same thing.
Application of the chain rule. Right. Okay, let's talk for a couple of minutes then about inertial frames. What is an inertial frame?
It's like a mental, it's like situational perspective where the observer is can be moving at a chosen speed relative to what we're observing, and we can determine impetus transfers, interactions, and that.
Okay, sort of. Got elements in there.
Would it, like what he was saying, would it also be like the frame where like there's no acceleration?
Okay.
Where, like all the bodies you'd be assuming is moving at a constant speed.
All right. First, so let's figure out what a frame is, right? Before we start figuring out what an inertial frame is, right? So, what is a frame?
Something with a picture.
Say again. What?
I don't know.
Something around a picture, Mr. Tremblay.
The point of view.
A point of view. Okay. Let's be a little bit more specific. A point of view could mean a lot of things
It's
these
what
days.
you can see from your point of view.
What you can see from your point of view, but
Your reference.
yeah, a reference. Yeah.
It's where you are and how you're moving relative to what you're observing.
Okay, so how you're moving, where you are and how you're moving. So we had different coordinate systems at different times. One of them was I could choose the origin of my coordinate system, say here, and then I measure the position of a fly buzzing around the room with respect to that, and so I'd have my 3 coordinates relative to that. Well, I could have chosen another coordinate system. I could have chosen the origin over here, and maybe x is this way and y hat's this way and z hat's this way, but I could still measure the coordinates of the same fly in a different coordinate system. That's an example of a different frame. But those 2 frames, the way I've chosen those 2 frames, they're not moving with respect to each other. So they're linked in a very simple way. Well, let's suppose I do something a little bit different. Now, let's suppose we have this cart with the air track of the cart moving on it, and we watched it from here while the carts are moving like that. Suppose I had a second air track with another cart moving on it, and I put a camera on that cart, and I took a movie of what was happening. That would be also a different coordinate system, a different frame. So that would be, we could imagine ourselves riding on that other cart. Would be easy to do on a bigger system. Suppose we have, that's why railroad tracks are, you usually see these described with railroad tracks and railroad cars. So you can imagine being on a railroad car that's moving down a track, and there's another track parallel to it. Something's happening on that track. You have 2 cars that are coming together, slamming together, something like that. So how does it look different if I view the system from standing beside the track, or if I'm on a railroad car that's moving? Okay, so that would be another frame. Now, what is an inertial frame then? It's a specific kind of frame. So we're on a frame standing on the Earth. But what is happening to us? It's imperceptible. We can't sense it. In fact, we're rotating, aren't we? We're spinning. We're on a merry-go-round. But it's difficult for us to detect that with our senses. The effects are so small for ordinary things. But where is something where you could detect the rotation of the Earth besides the Foucault pendulum? Where is something where you could detect the rotation of the Earth?
Shoot a rocket at somebody else.
Yeah, that's right.
Somebody else.
Shoot it. It doesn't have to be any. You don't have to have a target of a person out there. It would still work.
Like in general, like the
someone else out there.
We've had those
Well,
at the-
and that is actually how this effect was discovered, because people that would be out on the ocean, they're trying to shoot cannons miles. Even back in the 1700s, the cannons had long range. Now they're really long distance, and this is something you just shoot it that way. There's nothing propelling it. It's not a rocket, though. Let's don't talk about rockets. Let's just talk about cannonballs. Okay, just a projectile that doesn't have any propulsion. You just launch it, and then it falls. What happens to that if you shoot at something over a large distance? It gets deflected. It's the same thing that happens if you're trying to shoot somebody on the other side of the merry-go-round. Right? No rockets, just this is getting too brutal. You're trying to throw a ball to somebody on the other side of the merry-go-round.
Could you take this?
Oh, that's what you brought that in for. So you're trying to throw a ball to somebody on the other side of the merry-go-round. That's going to be kind of challenging, isn't it? If you throw it straight across while you're spinning, it's going to be deflected. And that's called the Coriolis Effect. And in order to make accurate naval artillery, they had to compensate for that and understand it. And this is where the understanding of the, I think, is where the understanding of rotating frames comes in. So that's not an inertial frame, because there appears to be some accelerations that are happening when there aren't any forces that are present. So what would be an inertial frame would be the rail car moving down the track without accelerating. So there, a non-inertial frame would be if the rail car has a rocket on it and it's starting to accelerate the rail car. That would be a non-inertial frame. But an inertial frame would be the rail car just moves down the track with uniform linear translation. Okay, so that's the distinction between an inertial frame and a non-inertial frame. The inertial frame would be a rail car which is moving down the tracks. Suppose we got so we have this these two carts coming in together. Suppose, or actually we had one where the cart, one was stationary, the other one was coming in. Target was at rest. The incident target comes in. The incident cart comes in. Suppose we were to view that from a frame which is moving with the center of mass. That's called the center of mass frame. What would that look like? Well, the two carts would come in together and bounce off, or they would come in together and stick. Right? So from the center of mass frame, it looks very simple. They either come in and bounce off, or they stick. So in the center of mass frame, the total momentum is 0, because the center of mass is at rest. And the total momentum is the sum of the momenta, and then the velocity of the center of mass is the total momentum divided by the total mass. So the velocity in the center of mass frame, the center of mass is not moving. That's what it means to be in the center of mass frame. Okay, so that's the distinction between inertial frames. Now, the principle that's important here is that there's nothing you can do within that frame to determine whether you are moving or not. You have to look outside of the frame. So if I put you on such a rail car and I close you up, I put a box around you and I close all the windows, you can't see outside. As long as the rail car is moving smoothly down the track, there's nothing you can do to determine that you're moving. There's no experiment that I can do inside. If I drop a ball, it'll fall straight down. But from outside, the ball is moving in a parabolic arc. Right? But from inside, it just moves straight down, which would be the same result that you would get if the car were not moving. It just falls straight down. So as long as it's not accelerating, all the experiments you can do within the car are going to yield the same result. So there's nothing you can do from within the car to determine whether or not you're moving. That's called the principle of relativity. It's attributed to Galileo, but not correctly. Who first came up with it? Buridan. Yeah, good old John. So, should be attributed to Buridan again. Another discovery of his. He put it in terms of a boat. You're standing inside of a ship below deck, and you're sailing on smooth ocean, and the wind is nice and constant. So you understand the idealizations he's talking about here, because anybody who's sailed knows that sailboats don't really move like this. But if you kind of get close to it. It's a really calm day, really steady wind, and so forth. Close the portholes. There's nothing you can do in